Okay, good evening, everybody. And welcome to another session of organic chemistry. In today's session, we are going to finish our discussion on the chemistry of alkynes, which of course is taken from chapter 9 of your text. Before we get the session started, just one announcement to make. Our own work assignment for the week is due on Sunday. That is Sunday, November the 3rd at 11 p.m. Okay. Okay, I'm sure you guys want to go over the quiz question that you just did. Okay, let's do that. Let's start with question 3. Gillian, can you go ahead and read this for us? Okay, thank you. Okay, so question 3 says, provide reagents for each of the following transformations. So this is a case of knowing your reagents. Remember, I keep telling you, you need to know what those reagents do. So let me write it here, just for emphasis. You need to know what the reagents do. Okay, once you know what the reagents do, you will find that most of organic chemistry is fairly simple. Okay, so what do we have there? We have this molecule here, butane. And what do we need to do? We need to go from one butane to this molecule here, which is a ketone. And as you can see here, we have the same number of carbon atoms in the starting material as we have in the product. So this is a case of changing from one functional group to another functional group. In other words, going from an alkyne to a methyl ketone. So now the question is, what reagent do we need to use in this particular transformation? What reagent? We have to transform this here to a methyl ketone. So what reagent do we need? Which one? Okay, very good. Okay, so you need mercury 2 as salt. So here you need to use mercury sulfate in the presence of dilute acid. Okay, this reagent here, mercury sulfate in the presence of dilute acid, will transform a terminal alkyne to a methyl ketone. Yes. Can you put H264 for the bottom? Yes, you could do that. In other words, instead of using the hydronium ion, you could write H2SO4. Yes. Okay, so this is just a case of knowing your reagents. Okay. Now keep in mind that our focus is on the carbon-carbon triple bond. Okay. So okay, about this one here, the same molecule, one butane. This time we want to go to an aldehyde. From one butane to this aldehyde here. So what reagent do we need?
That's going to be the HB.
Which one? Hydroboration oxidation. Very good. In other words, you do this. 1 borane, and you follow that up with hydrogen peroxide in basic medium. Okay? So this is once again a case of knowing your reagents. You just have to know those reagents, what they do. Okay. About C, this here. In this case, what we want to do here, keep in mind we want to go from this alkyne, carbon-carbon triple bond. And now, if we take a look at the product, we actually have one more carbon atom in the product than in the starting material. So this tells us we need to attach a carbon atom, a methyl group, to this carbon. So we are forming a new carbon-carbon bond. Okay? We are forming a new carbon-carbon bond. So what reagent do we need to do that? Which one?
KOH.
KOH? Okay, what does KOH do to this?
It puts a negative charge on the carbon and...
Okay, so you want to form the acetylide type anion. So this is a two-step process. So you form the potassium, quote and unquote, acetylide. Okay? So what this is doing is, this is an acid-base reaction in which the hydroxide here is essentially pulling off this hydrogen here. Of course, you are going to form water. And then in the process, you form the anion of the terminal alkyne. And then what do you do with that? You add what? The alkylating agent, and that would be what? Yes.
Instead of KOH, you can also use NaOH.
Yes, instead of KOH, you can use sodium amide. Okay. So now you add the alkylating agent, which is here. You could use methyl bromide. Okay. And what the methyl bromide will do is to react with this. Essentially, you are going to get a displacement of the bromide, and in so doing you are going to form a new carbon-carbon bond. Okay, so that is what this is here. So in essence, we could simply just do this. We could do this. Step 1, KOH, and then step 2, methyl bromide. We could do that. Okay, so that would be a two-step process. Okay, so in all of these cases here, it is a case of knowing what your reagents do. Of course, just as you said, we could also, instead of using the potassium hydroxide, we could also use sodium amide. In that case, you get this here. Okay. Plus, instead of water here, of course, you get ammonia. Okay, our focus is on the organic product at this point, so we don't need to worry about the ammonia. Okay, and then once you form this, then add the methyl bromide, or if you could actually use methyl chloride also, or methyl iodide, and then you get your product. Okay, so let us go to the next one. Okay. Okay, let's see here. Robert, can you read it for us? Okay, thank you. Okay, so here we have to give the IUPAC names for the following compounds. Okay, so let us try with start with A. Okay, if we take a look at A, compound A, this one here, what is the longest carbon chain that will be the base name for this molecule? The longest carbon chain. Anybody has an idea? 10? 10? Okay. Let us say this is my right hand and this is my left hand. Where do you want to start numbering? Okay, of course you want to start numbering so as to give the multiple bond the lowest combination of numbers. So you say the right side, very good. So we say this is 1, carbon 1, 2, 3, 4, 5, 6, 7, this is 8, this is 9, and this is carbon 10. So what that tells us is that we have substituents. The methyl is a substituent on carbon number 2. The ethyl is a substituent on carbon number 3. And this other ethyl is a substituent on carbon number 8. Okay, so what would be the name for this? What would be the name for this? Of course, because we have an alkene and you also have a carbon-carbon triple bond, we have to name this as an alkene first. Okay, so let us give this a try. Let's start with the substituents. Okay, so you have ethyl in 3 position, another ethyl in 8 position, and we have to follow alphabetical order. So that becomes 3H, right? Diethyl. Now what is next? 2-methyl, right? Then what is next? Indicate the position of the double bonds. Okay. And that is what? 1, 3, 7, right? Okay. And 9. Okay. 1, 3, 7, and 9. Then we say it's their car. Keep in mind this is coming from decane, so you remove the NE since we have multiple bonds. Deca, tetra. Ordinarily it would be tetraene, right? If we do not have the triple bond. Now that we have the triple bond, we remove the E ending. Remove this E here. Then we have hyphen. Now we want to indicate the position of the triple bond. And that is what? 5. How many we have? Only 1. Okay. 5I. Okay. So the name of this is 3,8-diethyl, 2-methyl, 1379, decatetraene, 5I. Okay. So everybody agree with that? Okay. Now let us start B. Okay, before we do the B, because what they've given you here, they have written this almost like a super condensed structure. When you have this kind of structure, I will advise you write it out in a semi-condensed structure. So that will make it easy for you. Okay, so let us rewrite this. You have 2 ethyl groups attached to this carbon. So I will start with this. The other ethyl group is here. And then that carbon is a double bond carbon. Then it's CH. Then we have a triple bond carbon attached to another CH. And this carbon is also attached to this methyl because carbon must be tetravalent. And then we have that carbon is also attached to the carbon-carbon triple bond. Okay, so the longest carbon chain in this molecule is what? That would be the base name. How many carbons? say 9?
That should be 9, right?
9, okay. So we start numbering from what side, right or left?
Right.
Right, okay, very good. So we say this is 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have 9 carbon in the base name. And now the branches are in positions 3, a methyl in position 3, and an ethyl in position 7. Okay. Okay, so let us give the name for this. Okay, let's name the substituents first. We have 7-ethyl, is that right?
Yep.
7-ethyl. Then I think 3-methyl. And now we begin to now indicate the position of the multiple bonds. So we indicate the double bond, right? Yes, you have a question?
Yeah. Why do we start from the right? Aren't we supposed to look at the double bond first?
Why do we start numbering from the right?
Yeah.
Because you have to give all of the multiple bonds the lowest combination of numbers.
So, but before you said that the double bond to express this.
Yes, if for example, if you start from both ends, and one double bond is in one end and triple bond is in the other end, and they could get the same number, then you give preference to the double bond. Okay, but in this case, if that is not the case, then you have to give the lowest combination of numbers to all of the double bonds, or all of the multiple bonds. Okay. Okay, so therefore we started numbering from the right. Okay, so what do we have? 7-ethyl, 3-methyl. Now we indicate the position of the double bond, right? Where is the position of the double bond?
That is
What, 6? Okay. Okay, and that is 9 carbon in the chain, so that becomes no ning. Now, since we have triple bond in here, we remove the E ending, and now we want to indicate the position of the triple bond, and the triple bond are in what position? 1, 4, right? Is that 1, 4? Okay, just a minute. 1, 4, di. Okay? Yes, go ahead. The bond behind carbon number this here? Okay. No, it's a triple bond. This one here. This carbon number 1. Okay. Okay. Let's go to the question number 1. Is that okay? Is that clear? Okay. Question number 1. Okay, let's see here. Okay, Ashanti? Yeah, can you read this for us? Okay, thank you. Okay, so what we have here, each of the following transformations may require one or more steps. In other words, it could be a multi-step synthesis. Provide the required reagents for each transformation. Okay, so here, what I'll be giving you here, we're simply giving you a generic alkyne. Starting from this alkyne, we wanted to go to each one of these classes of compounds. Notice what we have here. Our focus is the carbon-carbon triple bond, and this R here, this R here could be any alkyl group. It could be this. It could be a methyl. It could be a cyclohexyl. It could even be a very complex molecule, such as this steroid here. In each of those cases, the R will be this here. This will be your R, and here is your R. So the point here is, whenever we are dealing with the chemistry of each one of these functional groups, very often our focus is on that functional group. Okay? So in this case, our focus is on this carbon-carbon triple bond right here. Okay? Okay. Now, how do we go from here to each one of these here, focusing on this carbon-carbon triple bond? Let me go ahead and number each reaction so we know where we need to go over here. Let us say this is 1, 2, 3, 4, 5, 6, 7, and 8. Now, this is another case of knowing your reagent, but a little bit more than that also requires now that you begin to think critically. Okay, so in the first one, what do they want us to do? The first one, they want us to go from a carbon-carbon triple bond to an aldehyde. Okay? What reagent do we need for that? Going from, okay, now notice what has happened here. Notice what has happened here. You need to be very careful here. It's a little tricky. If you look at this is this R here. We have these two carbon right here, right? Now look at what you have here. You only have one carbon here attached to that R. So that means we have lost a carbon atom. That means we have lost a carbon atom. Do you know of any reagent that will take an alkyne directly to an aldehyde and at the same time losing this terminal carbon? Do you know of any reagent that will do that? I don't think you do. Okay? At least I have not given you any reagent that will do that. So that means this must be a multiple step reaction. Right? Okay? Now if that is the case, do you know of any reagent that will make an aldehyde? And from what? From what? Any reagent that will make an aldehyde, and from what class of compound? Okay, you know ozonolysis, right? You know carbon-carbon double bond, right, alkene? Okay, if you do ozonolysis with carbon-carbon double bond, what happens?
You get ketone and hydroxylic acid. You do ozonolysis with alkene.
Yes. If you have an alkene and you do ozonolysis, what do you get?
Ketones and carboxylic acid.
Ketones and carboxylic acid. No. No. What? Aldehyde. Exactly. You got to know your reagent. Okay, so let us do this. So these are the kind of things you have to think of in this coming exam. Okay? Because this is the kind of question you are going to be getting in the coming exam. Okay, so that means we need to form an alkene. We need to form an alkene. And what reagent will give us an alkene from an alkyne? What reagent will give us an alkene from an alkyne? We have two reagents. Which type of hydrogenation? We have two reagents that will do it. Lindlar, exactly. Okay, you could use Lindlar or sodium in ammonia. Okay, so if we have Lindlar with hydrogen, that will reduce a carbon-carbon triple bond to a carbon-carbon double bond. Okay? And then if you take the carbon-carbon double bond, you react with ozone followed by zinc in acid. You get an aldehyde. Okay, in this case, this other carbon here also becomes an aldehyde. So you actually, in this case, you get two aldehydes. So, but we don't need to worry about this one here, this formaldehyde. Okay, so this is the product they want us to make right here. So this is a two-step process. Of course, in the first step, convert the alkyne to alkene, and then in the next step, you oxidize the carbon-carbon double bond to an aldehyde. Yes.
So because it wasn't a triple bind, we can use BH3 over H264.
BH with what? With what?
With H2O2.
But I know with what starting material? BH3. That is hydration. BH3 is going to add water. Okay. Okay. Oh, I see what you're saying. No. Okay. Very good. Very good. Okay. I see what you're saying. In other words, if we add adulteration with alkyne, okay, do we form? Okay, but the problem here is we are losing a carbon atom. I see exactly what you're saying here. Okay, this is what you are saying. If you do this, step 1, BH3, and step 2. If we do that, this is what we are going to get. But that's not what they're asking us to do. You see? We have to lose this carbon here. We have to lose this carbon here. This is the product. You follow that? So that is why we cannot just use this. You use the adulteration oxidation. Because, yes, you are correct. The adulteration oxidation will convert a terminal alkyne to an aldehyde. But in this case, that is not the product they want us to make. We have too many carbons here. You follow that? Okay. Okay. Let us do, that is number 1. Let's go to number 2. So in this particular set of reaction, not only do you have to know what the reagents do, you also now begin to put together a series of reactions. So that is why you have to really think very critically. Okay? Okay, so let us do number 2. Number 2. Okay, what do we need to do for number 2, which is this here? Go from here. Okay? What are we doing here? Apparently we need to add the, let us assume that this carbon here is this carbon, right? And this carbon here is this carbon, okay? So apparently we are adding hydrogen chloride, but we're also adding 2 hydrogens. Okay, if you analyze the product, we are adding HCl. We are also adding 2 hydrogen atoms. Okay? You follow that? So that means that you have to do there are 2 separate processes that you need to undertake here. Okay, going from an alkyne, definitely we cannot go directly from the alkyne directly to this here. We cannot do that. We've got to do one reaction before we actually add the hydrogen chloride. Okay, so what will be the process here? Lindlar again, exactly. You could add Lindlar to form the alkene, or you could use, in this case, you could also use, let's use Lindlar. You could also use sodium in ammonia. Or sodium in ammonia. If you do that, of course we get the alkene. We get the alkene. And then from the alkene, what do we do? What reagent do we need? Exactly. Okay. And that will now be a Markovnikov addition of hydrogen chloride to the alkene, and that's a Markovnikov addition. Okay? Okay, so when you have this kind of problem in which you need to do more than one step synthesis, you need to analyze the process, starting from the starting material to the product. Yes.
What if you put,
okay. Okay. Okay, let's go to number 3. But that, I'm glad you are thinking though, that's good. That's what you need to do, you have to think. Okay. But I want to keep saying this, before you can think critically, you got to have the tools for you to think critically. In this case, the tools will be knowing what those reagents do. Okay, so for number 3, we want to make this primary alcohol here. Okay, from an alkyne. Based on the chemistry that you know now, do you know any reagent that will take an alkyne directly to an alcohol? No. No, you don't. But do you know how to make a primary alcohol for something else? From an alkene, exactly. Hydration. You know that addition of water to an alkene, that gives you a primary alcohol using the anti-Markovnikov addition, right? So you cannot forget all of those things. You need to keep all those in your toolbox. Okay. Okay, so what do? We need to make an alkene again. Okay, so we could use lithium in ammonia or sodium in ammonia. Or in this case, it doesn't really matter. We could also use hydrogen with Lindlar. Any one of those will work. You form your alkene, and then from the alkene, what reagent do you need to use to go from this here to this alcohol? This would be hydration, right? It's anti-Markovnikov addition of water, right? And what reagent do you need for that? BH3, okay, very good.
just have
So you use borane, hydroboration oxidation. Okay.
I was gonna say for the H2 Lindler, the NaNH3, lithium nitrate, ammonia.
Ammonia.
You know what I'm saying? I was gonna say, what do you want to say one equivalent H2 over metal catalyst, or is that wrong?
Oh no, you can't. No, that would not work. Those reactions, the hydrogen, regular hydrogen with platinum, it doesn't really work. You know, it goes all the way. So you don't use that. I mean, I will give you a little bit of credit, maybe 1 out of 10, but okay. Okay, so let's do number 4. Number 4, this one here. I'm sorry, that was number 3. Let me change that. So what we just did here, this was number 3. Okay. Number 4, which is this here. Okay, for number 4, what are they asking us to do here? You are forming a new carbon-carbon bond, right? In other words, what we're doing here, we're doing alkylation. And how do you do that? What reagent do you need for that? Can you go from this terminal alkyne to that? Yes. Why not? If you have your sodium amide, and that gives you this acetylide type anion. And then you take this acetylide ion here, you react with methyl bromide, and you alkylate this acetylide ion. So okay. So that is number 4. Okay, let us do 5. You got this? For 5, to this here. Okay, now they want us to go from, this should be fairly easy. Everybody should get this. Okay, what reagent do we need for that? Can we go directly from alkyne, terminal alkyne? Yes, we can do that. And what reagent? No, ozone is cleavable. Ozone will cleave. Mercury, exactly. You got to know what those reagents do. Once you know what the reagents do, these problems are really very easy. So you do mercury, any mercury 2 salt in the presence of dilute acid or sulfuric acid will be fine. Okay? Okay, what that will do, mercury 2 salt will convert a terminal alkyne, this here, to a methyl ketone. To a methyl ketone. And that's what we have here. This is a methyl ketone. Okay. Let us do number 6. I'm hoping that this will be a review for you. The reason I gave you this problem here, so you can use it to get to know what those reagents do. Okay, I'm hoping that this is what you guys are going to use this for. Okay, because the best way to know what the reagents do is to actually practice a lot of problems. Okay, number 6. Okay, so now they want us to go from this, an epoxide. Okay, do we know a reagent that will take an alkyne to an epoxide? No, you don't. But do you know how to make epoxide? How do we make epoxide? Exactly, from carbon-carbon double bond. So what that tells you, you need to make an alkene first. Okay? So by now you know how to make the alkene. Lindlar, I will use Lindlar in this case. Or you could use Lindlar, you could use lithium in ammonia, you could also use sodium in ammonia. Okay? You form your carbon-carbon double bond. So by now, everybody should begin to know what this reagent do as a result of what we are doing right now. And then what do? You go from an alkene to an epoxide. What reagent do we need to go from an alkene to an epoxide? MC, exactly. Very good. M-chloroparbenzoic acid, MCPBA. Okay?
I have a question.
Yes.
What if you like mix up the letters and put MPP and you know what?
Well, I think I will know what you. I know what you mean. As long as you say MC, okay. I think I will know what you mean. Okay, MCPBA. That is this molecule here. Or you could also give me the structure of the molecule. All right? That's M-chloro benzoic acid. So the acronym we use for this is MCPBA. Okay? Okay, what other reagent can we use for epoxidation? What other reagent can we use for epoxidation? Since we are doing some review here, you could also use this to epoxidize a carbon-carbon double bond. Okay, you could also use this, I would say, or two steps. Step 1, you form the bromohydrin, bromine water. The bromine water will give you bromohydrin. In other words, add bromine and OH across the carbon-carbon double bond. And then step 2, you add sodium hydroxide. This combination here will epoxidize a carbon-carbon double bond. Okay? So keep that in mind. Okay, it's about 7. I hope we have plenty of time to finish and go to chapter 10 today. Who said no? Okay, so let's go to 7. Okay, everybody got this? You notice I am taking my time today because we've actually finished chapter 9. Okay, so let us do 7. Okay. 7. Go from the carbon-carbon triple bond to an alkene. This should be easy. This is what we've been doing all evening. Right? What reagent you need for that? Exactly. We use sodium in ammonia, or if we use lithium in ammonia, or you could use hydrogen with Lindlar catalyst. Okay? Very good. Okay, let's do the last one. That should be easy also.
That's just hydrogen.
Yeah, exactly. Just your regular, your classic hydrogenation, yes.
So we're not getting metal and hydrogen.
H. Okay, so what do we need? We need to go to here. So all you need for that is just your regular catalytic hydrogenation with metal catalyst. You could use palladium over carbon or hydrogen with platinum. Okay, you could do that. Okay. Okay, so we've finished all of the problem set in your quiz. Okay, so now let us yes.
So second, instead of putting H2 over lemon, can you have put that or put one equivalent of that?
No.
How come?
It will not. It doesn't work.
You want to triple bond for double bond.
No, it doesn't. No, the hydrogen over regular catalyst doesn't work with that. It goes all the way. It's really difficult to control.
I thought yesterday you said you put one equivalent in it.
No, no. That would not work. I would not accept that. I will give you some partial credit, like I say, maybe 1 out of 10. But no, don't do that. It's too reactive. It's too reactive. It goes all the way. You cannot stop it.
But you say go all the way unless it says one equivalent. So
no, but you have to control it. I mean, okay. What I'm telling you now, don't do that. Okay, don't use one equivalent. Okay.
So when do you say?
If I do compound ABC, right? If I do compound ABC, and I tell you that compound A only reacted with one equivalent of hydrogen, so that is telling you only have one double bond in there. No, but not triple bond. You cannot do with triple bond. Okay. Anyway, let's move on. Okay. So let us go to. Okay, if you look at the chapter 9 that we have been discussing, all of the items in chapter 9, the topics in chapter 9, we have actually covered everything. So what I want to do now, let us do a little bit more problems. Under chapter 9, and then if we have a little bit more time, I will start to introduce you to chapter 10, which has to do with the chemistry of alkyl halides. Okay. Oh, I don't want to show you that. I didn't want to show you that. Okay. Okay, let's do this problem. Let's do this problem. How will you go from this here to here? How will you go from here to here? From this alkene to this aldehyde? Okay. No, not the mechanism. Give me the synthetic. Okay. The way I will ask you this here, I say provide the synthetic scheme for the following transformation. Nobody's asking you for mechanism. Okay? Provide the synthetic scheme for this transformation. In other words, all of the reactions that you are going to use to take this compound to this compound. Okay, we want to make a triple bond excellent. Very good. Why did you? That's good. How did you think of triple bond? You saw it already. You saw it already. Okay. So anyway, the rationale here, you think about it. Say, okay, there is no way you can take this carbon-carbon double bond. There is no way you can convert this carbon-carbon double bond to this aldehyde. In other words, what we want to do, this carbon here becomes this carbon of an aldehyde. Okay, this is an aldehyde right here. Okay, so for us to do that, there is no reaction and no reagent that will allow us to take a carbon-carbon double bond directly to here. So therefore, but we do know how to make aldehyde. Okay, you say, okay, we know how to make aldehyde from an alkyne. So what do I do? How do you make an alkyne from an alkane? How do you make an alkyne from alkane? Which one? No. Okay. How do you?
Oh, you have to do it in this
double dehydrohalogenation. First, we need to know these reactions. Okay. Okay. So what do we need? But to do that, the first thing you do, you have to get the dibromo compound first, right? Because that means you react this here, the carbon-carbon double bond with bromine. Okay, react with bromine. Oh, by the way, let me tell you now, very often you will see us, this part of the molecule here, and so many of you will say, well, that's a carbon, it contains carbon-carbon double bond. Now, if you recall when we did resonance, this molecule here, this part of the molecule here, we do not consider those as double bonds. They do not react as double bonds as a result of resonance. When we get to, I believe, next semester, we are going to discuss this molecule in detail. But this here will not react as if it contains double bond because of resonance, okay? So, if you see this, do not think of it as alkene. Okay, so now we have this. We are adding 2 bromine atoms to the carbon-carbon double bond, right? So this hydrogen here, and of course you have hydrogen here to start with. And then once you have this, then you do your dehydrohalogenation. If you use sodium amide, notice here, this is the second time we are using sodium amide. Sodium amide could deprotonate acetylene. It could also do dehydrohalogenation. Okay, so keep that in mind. Sodium amide. Sodium amide, that will give us this here. Okay, so this is dehydrohalogenation. Okay, remove two molecules of hydrogen bromide. Actually, you end up with 2 sodium bromide and 2 ammonia. But you don't need to worry about the inorganic product. Okay, so we form the alkyne, and then from the alkyne we go to here. React with borane, followed by hydrogen peroxide, and that will give you this here. Which is this here, okay? Okay, so in this case, you got to know your reagents, and then once you know your reagents, at this point you need to be able to put them together. And this is what we refer to as a synthetic scheme. Okay? The various reactions that we are going to use to go from the starting material to the product. This is not reaction mechanism. Okay?
So CHO can be written as
Huh?
CHO, the picture can be written as C double minus O.
Which one is that?
I'm saying the way you wrote it, the way the picture it can be written both ways.
This here? Yeah. Oh, yeah. This is just a condensed structure. This here. Okay. This is an aldehyde. This is just the condensed structure right here. Okay. But yeah, you could write it this way. Okay. So let us do another one. About give a synthetic scheme going from here. Let us call this compound A. Compound A to compound B. Give a synthetic scheme going from compound A to compound B. Okay, let's do some analysis here. Okay, we are going to form a trans alkene. This is a trans alkene. Okay, we also look at this here. If we say this carbon here, you say this is carbon 1 and this is carbon 2. But you look at this here, we are forming a new carbon-carbon bond. Assume this is carbon 1 and this is carbon 2. So what this tells you, you need to form a new carbon-carbon bond. So what would that tell you, therefore? You need to extend the carbon chain, right? So you only know one way of forming a new carbon-carbon bond right now, and that is using acetylide with methyl bromide or methyl iodide or methyl chloride. Okay, so that tells you then, therefore, you need to make the alkyne first, right? Okay, so let us make the alkyne. Once again, to make alkyne, you need a dibromo compound, because that is the only method we told you so far of making alkyne. So I do bromination of the alkene. Okay, and then after the bromination of alkene, then I do dehydrohalogenation again. You could either use for that potassium hydroxide or sodium amide. Okay, so once you form that alkyne, then what do you do? What do we do? What do we do now? What do we do now? Okay, we form the acetylide. I say step 1, sodium amide. That gives the acetylide. Then step 2, I do the alkylation. And that will give us this here. Okay. Now what do I do from there? Keep in mind, this is where we need to go. We need to form a trans alkene. Which one?
No, that's a 6.
That's a 6. Okay, you need lithium. Exactly. Okay. Folks, you need to know those reagents. Okay. Or lithium in ammonia. You use sodium in ammonia or lithium in ammonia. Okay. Okay, so these are the kind of problems that you should expect to get in the next exam. Okay, you are going to be doing a lot of synthesis. In other words, this is what we call synthesis. Okay? Yes.
You said sodium or lithium and ammonia. It's basically just an alkaline metal and ammonia, right? So
Which one?
It's just basically alkaline metal and ammonia, right? So J plus would work.
No, no, no. This is sodium. Say that again.
Alkaline metals, so any alkaline.
No, 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 not. Yeah, alkaline metal. Yeah, yes. Sodium. Yeah, generally we use sodium in ammonia or lithium in ammonia. Not thinking about potassium. Is that what you're saying?
I think so.
No, but just stick with sodium and lithium. Okay. Let us do one more. Everybody got this? Okay. Okay. Let us do a little. Go back. Okay. Okay, now this should be fairly simple. Suppose you have this type of problem. Okay, supply these reagents B's, E, and F, going from let us call this compound 1, let's call this 1, compound 2, compound 3, let's call this compound 4. Okay, we want to go from compound 1 to compound 2. What do we need to do here? What is happening here? If you look at this, how many carbons do we have in compound 1? 1, 2, 3. But here we have 1, 2, 3, 4, 5, right? So that means we need to add 2 more carbons. Okay, as you can see here, you have the acetylene already. Okay, so what do we need to do here? Okay, just based on what you see here, you have the acetylene at the end of the chain, so you could simply take this. You use sodium acetylide. Okay? Sodium acetylide reacting with this becomes your alkylating agent. This simply now will displace this. This will now act like your methyl bromide. Okay? That becomes your alkylating agent, and so that is how you get this. So B here, reagent B is sodium acetylide. You know how to make sodium acetylide by now. Okay? Starting from acetylene. Okay, about E, going from compound 2 to compound 3. What do we need to do? Forming a methyl ketone, right? Nothing is happening to this carbon-carbon double bond. So what reagent do we need? That should be simple.
We need
mercury. Very good, very good, very good. This is not what you don't think about this. You just know this.
Wait, so for number 1, you don't have to write like KOH, you have to write.
Yeah, you could write KOH and then, yeah, KOH with acetylene to form this. But if you just give me the sodium acetylide for here, I will take it. Okay? Huh?
If you're going to use sodium amide for this one?
Which one?
The first one.
Oh, the first one, to form the sodium amide with acetylene, yes. You have to make this.
You have to use acetylene.
Right, you have to start with acetylene. Okay, or potassium hydroxide. Okay, that will give you the sodium acetylide. Okay, here for E, all you need is mercury 2 salt with sulfuric acid or dilute acid to simply have the hydronium ion there. Okay, that will give you this here. Okay, that should be fairly simple, simple to everybody here. About going from 3 to 4, compound 3 to compound 4. What do we need to do here?
we're adding
Bromination, exactly. So this should be fairly simple. Bromination. Okay, so that is what we need to do for that. Yeah, you know, as you know, you could use a solvent, carbon tetrachloride or methylene chloride. Okay. Okay. Can we go to chapter 10 now? Let me give you a couple more problems. A couple more problems to help you out. Don't you? But you need problems, right? Oh, okay. It's time already. Okay, folks. I will see you. I will see you on Tuesday. When we come back on Tuesday, we are going to start with chapter 10. Huh? With problems. Okay. So anyway, I will see you on Tuesday. So enjoy the rest of enjoy your weekend. By the way, before you go, this is what I was going to tell you this. Okay, supposing I would have told you, this is very important, and then you will leave. Instead of giving you all of this, I could very well tell you to give me a synthetic scheme. Provide a synthetic scheme going from here to here, starting from acetylene. Keep that in mind. Without giving you all of this intermediate. Okay. Okay, so that would be a good question. Give me the synthetic scheme from here to here, starting from acetylene. Okay?